Welcome to Graph Algorithms. This chapter teaches three classic algorithms for weighted graphs: Dijkstra for shortest paths, Prem for a minimum spanning tree, and Kahn for topological sort. They look different, but they share the same machinery. All three use relaxation, a frontier of candidates, and a careful processing order. Let's start with why we need graph algorithms at all. We will look at three everyday questions that plain traversal cannot answer. Let's look at the goals for this chapter. By the end, you will be able to do four things. First, you can perform one relaxation. Relaxation just means lowering a vertex's best known distance when a shorter path appears. Second, you can choose Dijkstra's next vertex. You pick the frontier vertex with the smallest tentative distance. Third, you can grow Prem's minimum spanning tree. You pull the cheapest crossing edge from a heap frontier, one vertex at a time. Fourth, you can order tasks by dependency. You run Kahn's algorithm on an in-degree array. One idea ties the three problems together. You keep a tentative best answer for each vertex, and you improve it as better evidence arrives. Dijkstra improves a distance, Prem improves a cheapest connection cost, and Kahn's algorithm improves whether a vertex is ready yet. Let's look at three everyday questions. Each one is a question about a graph. The first is your phone's GPS, finding the fastest driving route from home to work. The second is the cheapest cabling to wire every house into the power grid. The third is ordering courses, so every prerequisite comes before the course that needs it. Each of these is a weighted question or an ordering question. Chapter 15's breadth first search and depth first search only answer whether you can reach a vertex and how. They never answer what a path costs or what must come first. Let's start with the GPS problem. Chapter 15's breadth first search finds a shortest path, but only in an unweighted graph. There, shortest means fewest edges. Real roads are not unweighted. Each road carries a travel time. A one-hop highway can take 60 minutes. 3 quick back streets can take only 30. So fewest turns and least time are different questions. Ask your phone for a route. It never counts turns, it counts minutes. Once edges carry weight, breadth first search solves the wrong problem. Let's watch breadth first search pick the slower road. We drive from home, marked H, to work. Marked W, every road is labeled with its travel time in minutes. Look at the graph. The red road goes straight from H to W in 60 minutes. Below it, 3 small roads go from H to A to B to W, and each one takes 10 minutes. Now predict the answer. Breadth first search counts edges, so it picks the single direct road. H to W, one hop, 60 minutes. That is the fewest hops. But look at the route it threw away. The path H to A to B to W is 3 hops, and it takes only 30 minutes. So breadth first search's shortest route takes twice as long. Once edges carry weight, fewest edges is the wrong answer. The fix has a name, Dijkstra. Dijkstra answers the weighted question that breadth first search cannot. It keeps a priority queue frontier. It always expands the cheapest reachable vertex next. It relaxes every edge out of that vertex. As soon as a cheaper way into a vertex appears, it lowers that vertex's best known distance. So least total weight replaces fewest edges. With a binary heap frontier, Dijkstra runs in big O of the quantity V plus E times log V that is fast enough to route across a city-scale road network in milliseconds. It is the engine inside every GPS. One warning. You may think Dijkstra works on any weighted graph, but it needs non-negative weights. A negative edge can beat a distance Dijkstra already marked final. That breaks its greedy rule that cheapest so far is settled. When negative weights are possible, use Bellman-Ford instead. The gap we saw with travel times applies to all three questions. Let's read the table row by row. For a cheapest route, breadth first search and depth first search give you fewest edges only. The edge weights are ignored. For the minimum total cost to connect everyone, they have no idea of connecting at least cost. There is no cost-aware tree building. For a valid task order that respects prerequisites, they give a visit order, not a dependency order. There is no must-come-before rule. So plain traversal ignores edge weights and cannot order dependencies. This chapter adds weight-aware and order-aware algorithms on top of the same adjacency list from chapter 14. The traversal code itself does not change.